Previously we talked about first order low pass filters, and so that means obviously that low pass filter characteristics can be achieved by a first order circuit. But sometimes your design requirements are such that they cannot be satisfied by a first order circuit. Okay, it would be too primitive for your design. So what you have to consider in such a case is that you have to go for higher order topologies. Okay, so that motivates us to say a few things on the second order low pass filters. The transfer function for a second order low pass filter has the following form. Okay, a degree zero numerator polynomial. We have simply k, and the denominator polynomial is expressed in terms of the following parameters: omega 0 square. Okay, an example topology would be the following. Okay, here we have the input voltage, and here we have the output voltage, where we collect the voltage from the terminals of the capacitor. Okay, so the frequency response corresponding to this transfer function is J omega equals k over omega 0 square minus omega square plus j 2 alpha omega 0 omega. Okay, so let's see what happens at very low frequencies and at very high frequencies, so that we'll be in order to convince ourselves that this really produces a low pass characteristics. So at low frequencies around 0, so what we have is first of all, numerator is constant. It's independent of the frequency omega. And as for the denominator, at low frequencies, this term and that term, they vanish, and what dominates the denominator is omega 0 square. Okay, so at low frequencies, therefore, the gain is magnitude of k divided by omega 0 square. Okay, so we see something, okay, significant at the output at low frequencies. Okay, so what about high frequencies? When the frequency is high, then this guy dominates the denominator, and clearly k over omega square, omega being very large, produces something very tiny. So at high frequencies, not much passes to the other side, which is also clear from this example, because at high frequencies, okay, the impedance is 1 over j omega c. So that means at high frequencies, the capacitor becomes more and more short circuit-like, and if it's short circuit, clearly we don't see much voltage across its terminals at high frequencies, whereas at low frequencies, capacitor behaves like an open circuit, and open circuit means there will be very little current flowing over this resistor and inductor. That means there will be very little voltage drop across here, so most of the input voltage will appear as the output voltage. Okay, so it's clear that therefore this topology produces a low pass characteristic, and since we have two dynamic components, it's a second order low pass filter. Okay, so let's talk about a few details about our low pass transfer function. For instance, what's the maximum gain that can be achieved, okay, and at what frequency it is achieved. Let's talk about that. Now, that's not for the bandpass filter. We were able to obtain that by simply rewriting H omega. It became obvious, but for the low pass transfer function, for the second order low pass case, it's not obvious what's the maximum value and when it's achieved. So it in fact depends on the value of alpha. Okay, for instance, for alpha small, and by small we mean whenever it's less than 1 over square root of 2, and note that alpha and omega 0, they're always positive. So whenever alpha is less than that, then hj omega max, the maximum value that the gain achieves, turns out to equal h0 magnitude divided by 2 alpha 1 minus alpha squared. Okay, and by h0 magnitude we mean what? Magnitude of k divided by omega 0 square. And this maximum value is attained at, occurs at omega, let's call it omega max, the frequency where the maximum is achieved. Okay, at omega 0 minus 1 minus 2 alpha squared. Okay, and as for large alpha values, and by large we mean alpha greater than or equal to 1 over square root of 2, we have hj omega max simply equals the magnitude at omega equals 0, that is the DC, it equals the DC gain, which is magnitude of k divided by omega 0 square. Okay, here's an important note. When alpha equals the border value, okay, alpha equals 1 over square root of 2, then hj omega 0 equals h0 divided by square root of 2. So that's easy to check. And h0 magnitude, when alpha equals 1 over square root of 2, is the maximum value that the gain can attain. So the maximum value divided by square root of 2 equals the value of the gain at frequency omega 0. So that's by definition the cutoff frequency. Okay, so when alpha equals 1 over square root of 2, omega 0 happens to be the cutoff frequency of our low pass filter. Okay, so right, so that means cutoff frequency equals omega 0 when alpha equals 1 over square root of 2. Okay, so let's sketch the low pass characteristics, the gain function for different values of alpha. Okay, so when alpha is large, and by large we mean alpha larger than 1 over square root of 2, then what we have is a monotonic shape. Okay, so the gain function is always decreasing, and it attains its maximum value at the lowest possible frequency, which is omega equals 0. Okay, so we have this shape. Omega 0 h j omega, and this is for alpha greater than or equal to 1 over square root of 2. If alpha is small, then we have something a little bit more interesting, in the sense that the maximum is attained not at 0 but somewhere in between. Okay, sometime later. And we know that it's a low pass filter, so we start already from something that's far away from 0. Okay, and then it increases for a while, and then it decreases. Okay, so this such a bump, like shape occurs if alpha is small. Okay, so alpha less than 1 over square root of 2. And according to what we have written down, this maximum is attained at the frequency omega 0 times square root of 1 minus 2 alpha squared. Omega 0, 1 minus 2 alpha squared. Okay, so let's say also a few things about the second order high pass filter. Okay, this time the transfer function is such that we have a double 0 at the origin. Okay, with the low pass characteristics, we didn't have any zeros. The origin was a degree 0 polynomial. It was a constant. Okay, so now we have k s squared over s squared plus 2 alpha omega 0 s plus omega 0 square. So that's the general expression for the transfer function of a second order high pass filter. And one way to achieve such characteristics would be through the following two-port. Okay, here we have input voltage, and this time we collect the output voltage from the terminals of the inductor. Now, why that's a high pass filter at low frequencies? Okay, so at low frequencies, that is frequencies close to the DC, so that we know that at DC steady state the inductor behaves like a short circuit, okay, or its impedance is G omega L. When omega is around 0, impedance is very tiny, so inductor behaves like a short circuit. So if it's like a short circuit, that means we will not see much as the voltage across its terminals. Okay, so at low frequencies, the output voltage is insignificant, and when the frequency is high, okay, again the impedance of the inductor G omega L. When omega is large, so that means impedance becomes larger and larger. So at very high frequencies, inductor starts behaving like an open circuit. Okay, if it behaves like an open circuit, so clearly most of the input voltage will appear across the terminals of the inductor. Okay, so that transfer function produces the following frequency response: H omega equals minus k omega square over omega 0 square minus omega square plus j2 alpha omega 0 omega. Okay, so that's RH G omega. From this expression, it's also clear why this produces a high pass filter characteristics at very low frequencies. The numerator disappears, it almost becomes 0. So, and the denominator is dominated by this omega 0 square term. So what we have is something very close to 0 divided by omega 0 squared, so that produces 0. So at low frequencies we don't see much for the gain. And at very high frequencies, then this guy dominates, okay, the denominator, and here we have the numerator, and their ratio is k. So at very high frequencies, the gain equals to magnitude of k. So we're far from 0. That's why this produces a high pass characteristic. Okay. Now again, the behavior or the shape of the gain function depends on whether alpha is small or large, and by small or large we mean alpha less than 1 over square root of 2 or larger than 1 over square root of 2. Note that both alpha and omega 0, they're positive real numbers. So when alpha is small, then hj omega max, the maximum value, the maximum gain that's attained, equals hj infinity over 2 alpha 1 minus alpha square. Okay, and hj infinity is the gain that in the limit h omega attains, okay, when omega goes to infinity, which is, as we have already discovered, which is the magnitude of k in this case. Okay, and this occurs at the frequency omega max, let's call it omega 0 over 1 minus 2 alpha square, and then you take the square root. Okay, so that's the frequency at which we attain the maximum. And when alpha is large, that is, if it's larger than 1 over square root of 2, then the gain function adopts a monotonic behavior. Therefore, it's constantly increasing, and when that's the case, the maximum is attained when omega tends to infinity. Okay, so h omega max equals hj infinity magnitude. Okay, and as with the case with the low pass, second order low pass filter, when alpha equals 1 over square root of 2, omega 0 once again becomes equal to the cutoff frequency. Okay, when alpha equals 1 over square root of 2, we have cutoff frequency equals the transfer function parameter omega 0. Okay, now as for the rough sketches of the gain function for the second order high pass filter, we have the following plots. Omega, hj, omega magnitude. Okay, so this is for, let's say, alpha greater than or equal to 1 over square root of 2. So when alpha is large, then the maximum is attained at infinity and the shape is monotonic. We start at, when omega equals 0, the gain is 0. So we start at 0 and we keep increasing and increasing. Okay. And we're converging toward the magnitude of k, okay, which appears in the numerator. So that's the monotonic case when the damping factor is small. Then all of a sudden the gain plot attains a bump, okay, and that maximum is attained at omega 0 divided by that denominator, omega 0 over 1 minus 2 alpha square. Okay, so this is the alpha less than 0.7 case. Okay, now the next thing that we introduce is the concept of resonant frequency. Okay, now we're going to introduce that and we will discover its relation to the center frequency for a bandpass filter. Okay, now consider some one port and let Z denote its driving point impedance. Okay, so one port and ZS is the input impedance or driving point impedance. Okay, now for this one port, for this circuit, the resonant frequency is defined as that it's the frequency or frequencies at which Zj omega, okay, generally a complex number, becomes purely real. Okay, so it's a very straightforward definition. The frequency or frequencies, okay, there may be more than one, the frequency omega 0 for which Zj omega, okay, the impedance in the phasor domain circuit is purely real. Okay, in other words, imaginary part of Zj omega is 0 is called the resonant frequency of one port N. Is called the resonant frequency of our circuit N. Okay, now important one-port constructions, especially for filter design, are series or parallel RLC topologies. Okay, and it's not difficult to see that for those simple circuits, okay, the resonant, well, I'm not going to tell the resonant frequency, it's an exercise, okay, but I will produce what at resonant frequency these Zj omega boils down to. Okay, so here's a very simple but important exercise. Show that at resonance, okay, which you should figure out. This series connection AB LCR is equivalent to just this resistance, and this resistance is the resistance of this resistor here in the original construction. Okay, and the exercise is figuring out omega 0, which to some of you is already obvious. Okay, so this means that at resonance, whatever that frequency is, this thing becomes or behaves like a short circuit, and then this circuit boils down to, or can be represented by the simple resistor with resistance R. Okay, and the dual case is the parallel construction. A, B. So at resonance, it turns out that this is equivalent to LCR, again to the a resistor whose resistance is the resistance of this resistor here, R. A and B. Again, you are to figure out that resonant frequency. Okay, so here at resonant frequency, this series LC piece behaves like a short circuit. Okay, so at resonance they become short circuit, and here what's happening is the dual thing. At resonance, this parallel connection behaves like a short circuit. Okay, so since it's short circuit, we can just take it out of the picture, and what remains is just this resistor here. Okay, so let's, in our next example, study the relation between the resonant frequency and the center frequency in a second order bandpass filter. So suppose this is our circuit. This time the input and output are currents. One over CS. Here we have LS, this is R, and let this voltage be V. Here, this current is our input, and we collect the output as the current flowing through the resistor R. Okay, that's I out. And the driving point impedance is denoted by Z of S. Okay, now for this circuit, let's compute both the transfer function for the given input and output, and also the driving point impedance seen by our input. So the input current equals voltage across the terms of resistor. Well, since everything is parallel, there is a single voltage, that's V over R. Okay, and excuse me, that was output. So the input, now the input current is, since this is driving point impedance in Z, it's simply that voltage, which is also the voltage that appears across the terms of our input, divided by the driving point impedance. So this is Z of S, whereas the output current is V of S over the resistance R. Okay, and then taking the ratio of I out to I in, we obtain the transfer function. When you take the ratio, the voltages, they cancel, and what we have is I out over I in, which is our transfer function, and that equals the driving point impedance divided by the resistance of the resistor through which we collect the output current. Okay, now how about H of S and Z of S? So let's compute them. Okay, Z of S is easy to compute. So what we have is, we have three components in parallel. Therefore, the overall admittance would be the sum of three admittances, and then the driving point impedance will be 1 over that equivalent admittance. So Z of S therefore equals 1 over the equivalent admittance, and equivalent admittance is the sum of individual admittances. The admittance of the capacitor is CS, and then we have 1 over LS and 1 over R. So that's our Z of S. And that equals 1 over C S over S squared plus 1 over RCS plus 1 over LC. Okay, so that's the impedance. How about the transfer function, H of S? All you have to do is take that impedance and divide by R. Then what we have is 1 over RCS, and then we have the same denominator as the impedance. And h of s equals 1 over RCS s squared plus 1 over RCS plus 1 over LC. Okay, clearly it is in the second order bandpass filter form, which we expressed in general parameter form as Ks over s squared plus 2 alpha omega 0 s plus omega 0 squared. Okay. And omega 0, which is 1 over square root of LC, was our center frequency for our bandpass filter. Now, let's compute using our definition of resonant frequency, the resonant frequency of this one port, okay? Namely, the frequency at which the driving point impedance becomes purely real. Okay? So Z j omega equals j omega over C minus omega squared plus 1 over LC plus j omega over RC. Okay? So from this it's clear that when omega minus omega square cancels this 1 over LC. Okay, so we have j over j times something divided by j times something, so the j's will cancel and we will have something purely real, and that frequency at which the impedance becomes purely real is clearly 1 over square root of LC. Okay, so from this we see that Z j omega evaluated at omega equals 1 over square root of LC equals R. Okay, so it's purely real. Okay, impedance is purely real at this frequency. Now, here we have our second order bandpass filter transfer function, from which we see that the center frequency is 1 over square root of LC, and here by looking at the impedance we see that the same frequency is also the resonant frequency. Okay, therefore the center frequency and the resonant frequency for this construction, they happen to be the same frequency. Okay, is the resonant frequency. Okay. Now, in our next example is about the so-called cascade connection of filters. Okay, now consider the two filters. Consider the two first order filters. Okay, now at first we consider them separately. Here we have our first filter. Okay, which is high pass plus minus V2, and we have our second filter, which is a low pass. Okay, R1 over CS and 1 over CS R. This is the input voltage to the first filter. V2 is the output voltage, okay, of the first filter. We also use the same notation to denote the input voltage to the second filter, and the output of the second filter is denoted by V3. Okay, now let's figure out the individual independent at this stage transfer functions, namely V2 over V1, that's the transfer function of the first filter, and V3 over V2, that's the transfer function of the second filter. Now H1 of S, which is V2 over V1, equals R over driving point impedance, which is R plus 1 over CS, which can be written as RCS over RCS plus 1. And H2 of S, which is V3 over V2, and that equals 1 over CS over R plus 1 over CS, and that equals 1 over RCS plus 1. Okay, now let's try to figure out the transfer function from V1 to V3 when the output of the first filter is connected as the input to the second filter. Okay. Namely, let's consider the following circuit, which is called the cascade connection of the first two topologies. Okay. Now, let's check the cascade connection. Okay. V1 1 over CS R. Okay, so this is the output port of your first filter, and then what you do is you connect that pair of terminals to the input port of your second filter. Okay, and ideally we would want to have the transfer function from V1 to V3 simply as the product of the individual transfer functions H1 and H2. Let's see whether that's the case or not. Okay, 1 over CS, and here we have R. And this voltage here is, okay, plus minus, is our voltage V2. Okay, now let's figure out the resulting transfer function H of S, which is the ratio of output voltage, which in this case is V3, to input voltage, which is V1. Let's figure that out. So, writing the node equation here gives us what? V2 minus V1 over 1 over CS plus V2 over R, and then this is open circuit, therefore finally this current is V2 over this equivalent impedance, which is R plus 1 over CS. Okay, by KCL that should produce 0. This can be rewritten as something times V2 equals something times V1, and that something is CS, and whereas this guy is CS plus 1 over R plus CS over RCS plus 1. Okay, and then from this we can obtain V2 over V1. So that produces V2 over V1, the ratio of this voltage to the input voltage V1, and that equals RCS plus 1 RCS, and then RCS plus 1 square plus RCS. Okay, now here we have the ratio V2 to V1, and then here we have the ratio V2 to V1 for the initial circuit where the two circuits are disconnected, and in this case they are connected. Now clearly H1 of S, the ratio V1 and V2 over V1, is not equal to the ratio in the cascaded circuit. And the reason is this ratio, when this ratio is computed, it's computed for the circuit where this port is open circuited, okay? Whereas in the cascade connection, it's not open circuited, but it's connected to this R1 over CS combination, okay? Therefore, we're talking about two different circuits, and because the circuits are different, clearly the ratios cannot be expected to be the same. So this does not equal, for the obvious reason, to H1 of S, that is the ratio of V2 to V1 in the disconnected case. Okay, and then because of this inequality, V3 over V1 in the connected case or in the cascade connection will not be equal to H1 times H2. Okay, now let's continue with our analysis in the cascaded circuit and obtain the final answer H of S. Now H of S equals V2 over V1 times V3 over V2. As for V3 over V2, we can use the transfer function we obtained from the disconnected case, because the second port of the second circuit is still open circuited. Okay, so as far as the V2 V3 relation is concerned, nothing has changed, so we can use the previous transfer function. So that equals V2 over V1 times H2 of S, and that equals RCS over RCS plus 1 square plus RCS. Okay, now this does not equal to RCS plus 1 square, which is the product of H1 and H2, okay, where H1 and H2 are for the disconnected case. Okay, so in summary, the cascade, the transfer function of the overall transfer function of the cascade connection does not equal to the product of individual transfer functions which we obtain when the filters were disconnected from one another. Okay, so does not equal in general the product of individual transfer functions. So this is a little, it's not a good news, because here we have, let's say you design a nice filter, okay, H1 of S, and then you also design another nice filter, H2 of S, and then you combine them, you take their product, and then the product is very nice, let's say, okay, it satisfies your design needs, and then you go to lab and obtain the circuit that would produce that product, H1 and H2. You connect them in cascade, but you figured out that, you see that H of S does not what shall we do in that case? Okay, what shall we do so that we obtain the transfer function that equals h1 times h2? The answer is coming from EE201, namely one can use a buffer in such cases. Okay, so let's end this lecture with answering that question. Okay, how to achieve h of s equals h1 of s times h2 of s. How to make the cascade transfer functions equal the product of the individual filter transfer functions. The answer is use buffer. Okay, that is, this is your first filter. Okay, then here you have your second filter. Okay, you have here a nice h1, here you have a nice h2, and you want the overall cascade connection to have the transfer function which equals the product of h1 and h2. Okay, this is v1, this is v3. And for that, what you should do is you should make sure that the second piece does not load down the first filter. Okay, so that means the first filter should still feel that its second port is open circuited, and that can be achieved by plus minus the following buffer, and then here you short circuit here. Okay, so thanks to this buffer, this voltage will appear here, but since there is no current escaping into the op-amp, this guy will still feel as if it's open circuited for the second port.